Lesson 1, Module 3, Student Page 4. Consider a sequence that follows a times pattern. So we saw earlier that when we had multiplication, it usually was a power of. And if we think about this, let's go ahead and let me make this a little easier to see. We have 1, 5, 25, and 125. This is 5 to the 1. This is 5 squared, and if we multiply 25 times 5, that's just 5 3 times. So we must have started at 5 to the 0. So we can see that our pattern is shifting only by the exponents. So if we're going to write a function notation for this one, f of n, the value of the term in the nth position will be 5 to the, and you notice that the first position is 1, second position, the first position is 0, second position is 1, so it's to the n minus 1 power. So if we subtract 1 for our power, we can get our correct answers. And what we want to do is we want to make sure we don't get ourselves in trouble, so we're going to start, in this case, with n equals 1. Using the formula, find the 10th term of the sequence. So f of 10 is going to equal 5 to the 10 minus 1, just replacing n with 10. 5 to the 9th, and 5 to the 9th is a huge number. It's a number we're going to get in our calculator. Because 5 to the 9th is 1,953,000. And then 125. That's a huge number, so we don't want to have to figure that out by ourselves. Next, we're going to graph. At the top of the page, the first term in our sequence is 1, the value of it. The value of the second term was 5. We multiplied by 5, so the third term had a value of 25. 125 is the next one, and 5 times 125 is 625. And we are going to graph these guys. You may have noticed the scale of this graph. We go from 100 to 200. So when we try to graph 1, 1, 1, 1 is really going to look like it's right on the graph. And honestly, 2, 5 is going to barely leap off that page. So we're going to do that. 325, well, that's about a quarter of the way up to 100, right? And then 4, it's kind of ugly, sorry. 4 is at 125, so another quarter of the way up. And then 5 is at 625. Another quarter of the way up. Notice that our curve, we've got a curve now. Things aren't quite the same. On to student page 5 now. This question number 4. Consider the sequence formed by the square numbers. So what we're saying is that this is a number that's 1 by 1. This is 2 by 2, 3 by 3, and 4 by 4. So we can see that we can get some square number answers. Basically, 1 squared, 2 squared, 3 squared. So if we were going to try to write the formulas for these, we could say the function of n would be to just take the position in the sequence and square it. And that would be a very simple solution. We can start with n equals 1. Using the formula, find the 50th term. Well, here again, here's another one of these. Oh, actually, I'm sorry, 50 isn't too bad. So we're going to look at 50 squared. Now, if it had been 2 to the 50th, I don't even think our calculator could have handled it. But this is just 50 times 50. And I think 5 times 5 is 25. And I just add those two zeros on there. That handles it. And what we find is that the 50th term is 2500. Now we're going to graph what the square numbers look like. Remember that we're just squaring the position of the term. So 1 gives us 1, 4, 9, 4 squared is 16, 25, 36. I figure I might as well go. It goes to 10 and I have plenty of room. 7, 49, 8 squared, 64, 81, and 10. This one's going to, or excuse me, 10 squared is 100. This one will be a little easier to graph than the last one. 1, 1, we can at least pop a little bit off. 2 gives us 4. 3 gives us 9. We're almost to 10. 4 gives us 16, a little over halfway up to 20. 5 gives us 25. Finally, one that's easy to find right in the middle. 6 gives us 36. 36 is closer to 40, just a smidge, than it is to 30. 7 gives us 49, that's easy to find. 8 gives us 64, about here. 9 gives us 81. And 10 gives us 100. Again, we don't have a straight line path, so when we're dealing with powers and multiplication, things change. Now we're going to finish with student page 6. All right, a standard letter size piece of paper has a length of 8.5 by 11 inches. Find the area of one piece of paper. Well, area is just length times width. I like to multiply the lazy way. 1 times 8.5 is 8.5. And 10 times 8.5 is 85. What we find out is that a standard piece of paper is, well, it's 0.53. It has a square area of 93.5 inches squared. If the paper were folded in half, what would be the area of the resulting triangle? Well, let's see. 93.5 divided by 2. We get 4. I'm just doing the long division here. Some of you, it's been a long time since you've seen it. That goes in 6 times minus 12 gives us 1.5. So 2 goes into 1.5, 7, 5. 46.75 would be the area of the paper folded in half. If we were to fold it in half again, it would be sort of like going that, well, it says what's the sequence to determine this. So what happened was, for the first fold, f of 1, we multiplied 93.5 times 1/2. If we wanted to know f of 2, we'd have to multiply 93.5 times that 1/2 times half again. And I hope you see where this is going. F of 3 would be 93 times 0.5. I don't want that 0.5, but it's going to be messy no matter what I do. Times 1/2 times 1/2 times 1/2. So it looks like what we have is 1 1/2, 2 1/2. It looks like the times we multiply by 1/2 match our position in the sequence. That means we can say the function of n for the number of folds would be 93.5 times 1/2 to the n. We got a formula. Okay, so nothing in life is easy, and we want to know what would be the area after 7 folds. It's going to get pretty small if we fold it up 7 times. So we got f to the n equals 93.5 times 1/2 to the 7th power. That means it's 1/2 times 1/2 times 1/2 out 7 times. Well, let me tell you something. 93.5 times 1/2, 1/2 to the 7th power, 1 to the 7th is 1, but 2 to the 7th is 128. So we're going to divide 0.5 times 128 means 1 over 128 is 93.5 divided by 128. Can you see that the numerator is smaller than 128? So we're expecting a value less than 1. And what we do is we find out it's 0.7304. You don't really want to know. 6875. So folding a piece of paper in half 7 times is going to give you a very small number.